Hello and welcome back. Today, not on the bench, is my right leg. Not posted for a while, the reason being that I had a motorbike accident. So as mentioned, today not on the bench is my right leg. We're just going to have a quick look at that. If you're a bit squeamish and don't like cuts and things like that, look away now. So, as you can see, we've got the Frankenstein style sort of aesthetic going off here. A few staples in the old holding the old wound together. And so in a nutshell, right, you can look again now if you what's it, all the horrible bits are gone. Yeah, so what happened was I had a motorbike accident, broke me right tibia and fractured me left pelvis in 4 places. So obviously been in hospital, been a bit preoccupied and not posted for a while. I'll just put my old leg down. So yeah, getting about is difficult. And with the aid of these pieces of bits here, I shall recreate the accident. So, a little country road, well not so little, an A road. This is me on a motorbike, this is a bus, this is a car that I hit. So we've gone round a few bends here and everything. The bus is slowing down. I'm thinking, oh for fuck's sake, right, I'm off ski. So I think I'm a bit further back here somewhere. I clocked the road ahead, everything's clear, pulled out and accelerated. Not realising that the bus had slowed down to allow this vehicle to turn right. So as I'm fucking flying down here, I don't know, I must have been going 50, 60. The car turned like that. I realised I was in deep shit, managed to slam the back anchors on, and I think I went sideways down the road. He's continuing on like that, wallop, hit him like that, bang like that. My left leg got stuck underneath the sort of car sill and twisted. I think that's how I sort of fractured my pelvis a bit. I'm not quite sure how I broke my right leg. I can't really remember. So anyway, I was banging on the bloody car saying, "Wait, can you reverse back? Because I can't get me freaking leg out." I think he reversed back a bit. I fell off the bike, and the bike fell over. I lay on the ground. I tried to get up, and I realised I was in serious shit. The gaffers came, the police came, the ambulance came. They had a look at me. I said I was, yes, obviously in pain. I knew, I knew I'd done something like, but yeah. The ambulance took me home because I didn't want to go to hospital. I just wanted to get home. I don't think I was quite thinking right. So yeah, I went home, spent the day just sitting in a chair trying to get up with a stick, and it was really painful. I was seeing stars and all the rest of it. And anyway, my daughter came home later on and I went to hospital for 10 days and they operated on the old right knee. Look at these lovely legs. I've been wowing the nurses at the hospital with these. Look at them legs. Hey. Yeah, went to hospital for 10 days. They put a plate, I think, in there and some screws. When I came out of when the pain medication wore off, I was in real pain. I had a really bad night. Anywho, I am working on electronics, or I was doing prior to having the crash. This being on the bench, we've got sort of a test set up for the next amp, which will be using these output transformers that I got off my mate Joe in Australia. Really good output transformers. He knows what he's doing. So these were originally designed for 4 EL34s, push-pull, ultra linear. I haven't got any EL34s, however I have got some 807s. So we're going to try some 4807s, but get the old data sheets here. Try running them in pushball class A. And so here we've got a load of various kind of DC conditions, and here we've got our output load impedance. So let's just touch on amplifier design. How do I go about it? I sort of wing it really. I don't really do a lot of calculations or anything like that, although obviously there are some involved. You know, we've got to have some idea of what we need. But how do I go about it? Well, we'll try like 600 volts on the HT with a screen grid at 300 volts. So that means we need obviously 300 volt source. 300 600. Well, 300 is halfway between 0 and 600. So I started winding this big toroid over here. This is a 1.2 kVA toroid, far too big for the job, but it's what I've got. This basically started out in a big spectrum analyzer. It had secondaries for something like, I don't know, 60 volts at 14 amps, something stupid like that. I took those off and I've wound a 350 volt secondary out of pretty heavy gauge wire so that we can kick out about 1 amps if needed be. The reason it needs to be so bloody big, 1 amp at 600 volts eventually probably, is because I'm going to use a lot of capacitance. I have some big 1100 microfarad capacitors, although they're only rated at 450 volts. But something like that, that's the idea at the moment. And we've got a choke here which is about 30 millihenries. Also over here we've got a big transformer that came out of one of the tech scopes. But let's get back to the power transformer winding. I've only wound this one secondary on so far because I don't want to put the next winding on until I know what voltage that I need. So we go back to the data sheet. So you want to build a valve amplifier and you want to know what sort of power transformer you need. Well, it's a case of doing a few simple calculations. Say for instance in this instance we need 600 volts at 80 or 500 at 100, so we're somewhere around there. Let's just say 600 at 100 milliamps. This is per 2 valves, so you're talking 4 valves, so we've got to double that, and if we're talking the stereo amplifier we've got to double that again. So to find the what sort of VA we need, what sort of watt transformer we need for a start, it's just a matter of so first we need to figure out what we need as a rough idea. So we've got 600 volts DC. Well, we can't use that DC winding and then times it by the current because that's wrong. The AC that comes off the power transformer will be lower. So what we need then is to sort of divide that 600 volt. We've got 600. Now you can divide it by 1.414, which is the correct what do you call it, numerator to get volts RMS, because this is peak, I think. I don't know, one of those. Anyway, what I do, I times it by 1, oh no, sorry, I divide it by 1.35 because that takes into account losses like, you know, the diode, bridge rectifier, things of that nature, and this will give us a rough figure, and that equals 444 volts. And I usually add about 20 volts onto that, so 444, let's call that 460, let's call that 465, and then we've got our current. So we said we've got to double it, and then we've got to double that figure again. So I'm going to go for the biggest figure to give me some headroom. So I'm going to say 100 milliamps. This is quiescent voltage, this is. If this was a class AB1 amplifier, we would have to times that by 1.5. Even in this class A amplifier, the current will go up, as it says, look here. Plate current, but quiescent, no signal, 80. Plate current maximum signal, 150. Well, how can that be in class A? Class A, it's just not supposed to move, isn't it? It doesn't, current shouldn't go up or down, but it does. It puzzled me, this did, because on the 807 datasheet, the STC application report, which is the best datasheet to get for the 807, if you look at other charts for class A, single-ended and things of that nature, it hasn't got this two figures. But I think what's happening here is that because the valve starts to turn into a diode, and so we get some current flow. I think that's what it is. So hence we get a bigger figure, 150. So yeah, we'd probably best go for that, hadn't we? Which basically, if we was taking 100 milliamps times 1.5, we've got to treat it as a class AB stage, 150. Yeah? So let's say 150. So we said 465. I hope you're getting this. I hope I'm not going too quick. Cancel. 465 times by 150. Double it again, 300. And double that, that's 600 times by 0. I'm going to delete that. 0.6. So you can see how I got this 1 amp winding for the secondary. I'm making sure I've got some headroom, because the other thing I found is if you're winging it, if you're doing it sort of off the cuff, it's best to have a bit of wriggle room. Anyway, what's it? That gives us 279. So that would be 279 VA. Okay. Now then, we've got to heat the thing. We've got 8 807s at 0.9 900 milliamps. So let's just call it 1 amp each. So that's 8 amps. And let's make our life simpler and say that instead of 6.3 volts, we're going to say 7 volts. 7 times 8, 56, isn't it? So we write that down. 56 VA. And so we go through the whole amp. We're going to need a bias winding, so we're aiming for something like, this is just from experience because I know it works, 100 volts DC. Again, we divide, hold on. We'll divide that by 1.35 to get 74. We don't really need to bung 20 volts on that. Maybe another 10. So let's say 84 volts. Let's just say 80 volts. Cancel 80. And I want plenty of headroom. Times by 0.2. 200 milliamps. 16 VA for the bias winding, because this is going to be fixed bias. We've got some other valves there, 2 valves to say a voltage amplifier and a phase splitter. 6SN7 is 600 milliamps, 6.3 at 600 milliamps, and ECC82 or something like that is half that. But let's just give ourselves plenty of wiggle room. So let's call that 4 amps. 7 times 4, 28 VA. Obviously the preamp sort of and phase splitter will take a bit of current, but it's only a few tens of milliamps if that, so we can sort of ignore that. Obviously if you've got a more complex pre sort of driver situation going on, then you might have to add a bit more. But let's just say that that's what we've got for now. Alright, so let's add all those up. 279, let's just call that 280. Add 56, let's just call that, well no, let's 56. Add 16. Add 28. 380 VA. Now then, we want to add a bit on. I usually add about 10%, and that's to be generous. So I would add something like 10%, which would be 38 VA, wouldn't it, in this case? So we would need something like a 325 VA amplifier. Why add some on? You've got the core losses and you've got the winding losses. So you've probably got something like 2% core loss and a 5% winding losses. The winding loss is basically the copper as a resistance. There's a lot of copper on a transformer this size. It's going to get, some of that is going to get lost in heat, because there's going to be some resistance. When you've got resistance, you get heat. So I would add, like I say, 10%. Hope that all makes sense. It's just a very quick, dirty sort of way of calculating it. The thing is to obviously consult your data sheet. Like I say, I'm winging it here. I did do a load line to give me some rough idea, but I don't really find the load line that useful. Not for an output stage. I just bung it on the bench, do a prototype and test it really. I mean, it would tell you what distortion you get and things of that nature, but not really worth bothering with, I don't think, but there we go. So it's all a bit, how you doing? Well, we've basically got a very simple output stage. Each 807 has a small resistor going to its cathode so that we can sense the anode current, cathode current. Each cathode has a small resistor, in this case 1.2 R, because that's what I had, going to the cathode so we can sense the cathode current. We've got a screen grid stopper, which in this case is a 220R. I just went into my used resistor stash up here, because when I build in amps I saved the resistors that I've used in the past. That's just what I had. As a rough rule, for the control grid stoppers, you usually have it 10 times bigger than your screen grid stopper. So in this case I'm going for 2K2 for the control grid. Then we've got two 100k going to each of the 807s, but as they're sort of strapped in parallel, then that's about 50k. Again, I just used pretty much what I had to hand. I know from past experience that we need something low. It's no good using 220k. On the data sheet it will give you the lowest that you can have. It sort of goes like this. For cathode biased it's a little bit higher. It's sort of the highest value that you can use. For fixed bias it's a bit lower, and because we're in parallel here we have to halve that. So say if in fixed biased it was something like 100k, well obviously we halve it, hence our 50k. It isn't that figure, but that's what I'm using, just as because of what I had. Got two big 470 nanofarad 630 volt decoupling caps. We've got a couple of 10k Bourne's pots, and they are to basically set the bias to each side of the output stage, each side of the push-pull, if you're with me. Not really necessary, but I do like to have a bit of adjustment so that we can dial that in. We can either dial it in so that we get as little harmonic distortion as possible, or in this case I want to play about with it to actually increase distortion if I want to. We've got our output transformer, which will obviously be connected to that with our top caps. We've got our 350 volts coming off this transformer, which then goes into these two capacitors here. So we've basically got a CLC filter. As I mentioned, this is 30 milliamps. These are the only chokes I got, but they're rated at about 3 amps because these are swinging chokes. I've got another smaller but still quite a hefty transformer here. That's for our bias supply. We've just got a bridge rectifier tacked onto the secondary there, and two big sort of capacitors, 220 to 470 microfarads, 150. So we've got two RC filters there, and we've got a pot so that we can adjust what bias we want here. We want something like minus 29 volts. This big tech transformer here, that's going to provide our HT, or I might use my big power supply. And then the last thing that I've done is to build a very simple regulated supply for these screen grids, and this is it. Very simple. It's a little bit more complex than some of the simple circuits you out there that just use a MOSFET and what have you, but this has got a little bit of fold back and a little bit of a sort of voltage reference. So we start off over here. We've got a 100U cap, got a HT coming in or whatever. We've got a couple of diodes there. That sets the DC conditions for the base of this MPSA 92. And we've got this big resistor there that obviously sets the conditions for the base. This wonker here sets the emitter voltage, so obviously there must be something like 2 volt diode drops. What's that, 0.6 is it, or 0.4? So it's about a volt. So if there's a volt there, and there's got to be what's it, 0.6 less, hasn't there? So a little bit less than a volt on the emitter. The collector goes over here to the collector of an MPSA 42. Its emitter is fixed by this 12 volt Zener, and then we just got a 100 U decoupling cap. Both the collectors go to what I've got here. I've got just a big MOSFET, which is a 24N60, I think, 600 volts MOSFET. And then the base of this MPSA 42, this is what we use to set the output voltage of this regulator. 330k drop-in resistor, and then here it says 10k and 22k. What I've got is a 30k preset and a 47k fixed resistor, which I found yesterday by experiment. So I've just got to solder that on properly, and then hopefully we can fit some valves and start a bit of testing. I've got to obviously go over everything a lot before. As you can see, it does look very how you're doing. Yeah, as mentioned, everything is a bit sort of how you're doing. A few sort of leads holding everything, a few jump leads holding everything together. But I have powered it up prior to the motorbike crash, and it was all working okay. I did a little bit of testing using the HP 8903B audio analyzer and using ARTA on the PC to monitor, using the FFT plot to monitor the harmonic distortion content, and then I was just using the big old bench power supply to give me a HT of 500 volts. I'm wary of using this stacked on top of the 300 volts or the 350 volts because I blew it up last time when we were mucking about with the Firetrons doing a similar sort of thing. So yeah, so I can only test it up to about 500 volts. Don't know if there's much more to say really. This video's a bit long. I've sort of mashed together a bit of footage that I recorded after the motorbike crash and a bit I recorded prior to the motorbike crash. Hopefully though soon we'll get to testing all this and mucking about and yeah, having a look at various, you know, harmonics that we throw up and maybe even bunging a speaker and a bit of music on to have a listen to it. Anyway, that's all for now. Hope you're keeping alright out there. Take care of yourselves and ta-ra for now.